All right, welcome to lecture 11, which will be a relatively short one, where we talk about diene, types of dienes, and also in their stability and the stability of allylic and benzylic carbocations, which are resonance stabilized systems, and then just a general review of resonance, because it has indeed been a while, and making sure everyone's on the same foot when it comes to resonance will be really helpful in the future lectures. There are also some problems interspersed that you can work on your own, and we'll discuss in class next week. Next time, so after this lecture, you will be ready to tackle two reactions from chapter 16. One reaction is addition of hydrogen halides to dienes. And these will bring up two new concepts, which is thermodynamic versus kinetic control in reactions. This will be thermodynamic versus kinetic control. And we'll also look at the Diels-Alder reaction, which, if you're in the laboratory course, we started on that reaction this week. Okay, so let's look at the different types of dienes. And so anything that has two alkenes is going to be called a diene. Usually we look at isolated dienes. So this first example here shows isolated dienes, and they have alkenes that are separated by one or more sp3 hybridized carbons. So those sp3 carbons interrupt any chance of having overlapping pi systems. And then there's also occasionally you'll have allenes, or sometimes called cumulines, which are 1,2 dienes. And so those, of course, feature an sp hybridized carbons. These tend to be less stable than either isolated dienes or conjugated dienes. And so the last case, and which is the focus of this chapter, are conjugated dienes, so number 3 here. And these have essentially alternating double, single, double bonds. And so all of these atoms all along here are sp2 hybridized, which allows us to have resonance throughout this entire system. So how stable are these? Well, to look at that, let's look at the heat of hydrogenation, right? And if you remember, the heat of hydrogenation is the amount of heat given off when you hydrogenate a double bond and convert it to an alkene. So if we look at pent-1-ene, when we hydrogenate that to pentane, we get off 30.1 kilocalories per mole of energy. If I take the diene, penta-1,4-diene, and reduce that to the same alkane, I get 60.2, right? So there's 30.1 kcals per mole in one bond. If we divide 60.2 by 2, we get 30.1 per pi bond. But look what happens when we go to the 1,3-diene, right? Notice this is a conjugated diene because they're 1,3. These both make the same product, but now we're only getting 53.7 kcals per mole. So this tells us that less energy is stored in those pi bonds. But one argument you can make, though, is that this has penta-1,3-diene has a disubstituted alkene. and one monosubstituted. Whereas penta 1,2-diene just has 2 monosubstituted alkenes. So maybe that's the only reason for this difference, because it's more stable. So to see if that's important or not, we could do the experiment once again with E-hexa 1,4-diene, which is now an isolated diene that has 1 disubstituted alkene and 1 monosubstituted alkene. And what do we see here? We see that we get more energy than in the conjugated diene. So this is less stable than the conjugated diene. And it's not just a matter of substitution. So there's something interesting going on here with conjugated dienes in terms of stability. So let's look at this more. If you recall, there are a couple of factors that can affect alkene stability. Of course, as we've just been talking about, number of substituents, and also trans versus cis. Right, so for example, this alkene is more stable than acetylene. And in general, what makes an alkene more stable? When it has minimal steric interactions and maximal electron density. All right, so those are the two things that can make this alkene more stable. But what we saw previously is that in conjugated dienes, there is something more. There is a special stability associated with conjugated dienes. These are dienes of the type where there's the alternating double, single, double bonds. So now that you have seen this, you should be able to explain why we see this reaction from the diene on the left upon treatment with H2SO4 gets converted to the diene on the right. And based on what you know about alkene addition reactions, you should be able to suggest a mechanism for this reaction. So I will leave that to you. We can discuss this next class. So what is the rationale for this increased stability of conjugated dienes? The first argument we're going to use, and really the only one we'll discuss, is valence bond theory, which is really just thinking about hybrid orbitals. So if we look at butane, which is fully saturated, these bonds are all formed by overlap of sp3 orbitals. By comparison, 1,3-butadiene here is formed by overlap of sp2 orbitals, right? And we can see this when we look at the bond lengths. In 1,3-butadiene, this bond length is 147 picometers, whereas in butane, it's 153. So that bond has higher S character in those two sp2 bonding orbitals, so this makes the bond shorter and stronger. And if we look at the resonance structure here for butadiene. So if we move pi electrons into the previous space, we have a double bond right here between these two bonds. So right here we see partial double bond character. And so this means that the electrons are spread out. Now, and this bond is stronger. I will point out that this is not really the best explanation for this increased stability. To explain this better, we really have to turn to molecular orbital theory, which you probably talked about briefly in general chemistry. And we will revisit it at some point, but that really is a better explanation for this process. We will talk about it when we talk about UV spectroscopy. We now turn our attention to other conjugated systems, and those of allylic and benzylic carbocations. And these conjugated carbocations are especially stable. And so the general trend in cation stability is that methyl radicals are least stable. Primary cations are next stable, and even more stable are secondary cations and the allylic cation, which we talked about last time, right? And that, of course, has a resonance structure, right, where we can delocalize the positive charge to this other carbon. These are less stable still than tertiary carbocations and substituted allylic. So these are systems where it's both allylic and secondary or tertiary on the carbocation. So this system I've just drawn right here is both secondary and allylic. And these are more stable than, or similarly stable are benzylic cations, right? And those are the ones that are adjacent to a benzene ring. And so the example I've just drawn is secondary and benzylic. So this is just a general trend of the hierarchy. So thinking about what makes carbocations more stable and these effects of conjugation, now you should be able to think about this question, this hydrohalogenation of, or HX addition to the alkene shown. There is only one of the possible constitutional isomer forms, and you should be able to think about and explain why that is. Okay, so there's going to be a lot of resonance coming up. So just a few reminders about drawing resonance structures. One is, of course, you can only move electrons. You can only have lone pairs, move lone pairs that are there, or electrons in double and triple bonds. These are all pi electrons. You can't break sigma bonds. And then also the total number of electrons does not change, and neither does the net charge. Right, so if you have a net negative charge in one resonance structure, you have to have a net negative charge in all of them. And best resonance contributors have complete octets, if possible, right? Sometimes, for example, carbocations do not have complete octets, and there's nothing you can do about it. They also have minimal charge separation, right? So fewest numbers of charges, or of charged atoms. And if there's a negative charge, for example, it goes on the more electronegative atom. And that's a better contributor. So a better resonance contributor we think of as representing or resembling the actual distribution of electrons in a molecule better than others. So here's just, I'm going to work some examples of some problems where we draw all resonance forms and indicate which is the major contributor. And then we'll draw the resonance hybrid. That is kind of the net picture of how the electron distribution and charge distribution is in a molecule, and we'll indicate hybridization in geometry. So here in this first example, notice we have lone pairs next to a double bond. So these can move to this carbon because those the electrons have somewhere to go. So the resultant resonance structure, resonance form, now has double bond character here, and I'm going to add in the missing electrons. Negative charge up here, and a double bond down here, right? And so we have, these are our two resonance forms, and this one, if you recall, we call this ion the enolate ion, but this has negative charge on the oxygen, so we would consider this the more major contributor because the negative charge is on the more electronegative atom. And the resonance hybrid would have the structure shown, CH2O, right, and then partial bonds here, partial double bond there, partial negative charge on this carbon, partial negative charge on this oxygen. So that is the resonance hybrid. And hybridization in geometry, well, it's got to be the same on either one. So we know that the carbon has to be sp2 hybridized because it has a double bond. It means those electrons have to be pi electrons. This is sp2. This oxygen must also be sp2. And this carbon right here is not involved in that system because it's sp3 hybridized. All right, so there's the first example. All right, let's look at the next one. So notice we have lone pairs next to a cation. So those lone pairs can go and form a double bond to carbon. And we get a positive charge on nitrogen. If we draw that was the first part, if we draw the resonance contributor, or the resonance hybrid, we now have a system that has partial charge on both the nitrogen and the carbon. So partial positive here and partial positive charge on nitrogen. And in terms of which contributor is major, it's actually going to be this one because it has a complete octet. Okay, and these atoms are going to be, nitrogen has to be sp2 because it's making a double bond. This carbon is a carbocation and forms a double bond, so it must also be sp2. And this carbon is not involved and is sp3 hybridized. And remember that sp2 hybridized atoms are planar and have 120-degree bond angles. sp3 hybridized atoms tend to be tetrahedral and have 109 or close to 109-degree bond angles. All right, next example, we have nitrogen next to a sp2 hybridized carbon, a carbon with double bonds. And now these electrons have to go somewhere in this pi bond. And so they can move to the carbocation. And so the resulting resonance contributor has a single bond here, positive charge on nitrogen, double bond character here, CH2, and so we end up with, oops, forgot an H. When we think about our resonance hybrid, we're going to have NH2 to carbon to CH2. And this will have a partial bond here, partial bond here, partial double bond here, with partial positive charge on this carbon, partial positive charge on this on nitrogen, and partial positive charge on carbon. And so notice that now that electron density is spread across the entire system. And if we label the hybridization, this is going to be sp2, 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 and sp2. So all of those atoms involved in this resonance system are sp2 hybridized and planar. Okay, last example here is actually the allyl cation, right? These pi electrons can move and be shared with the opposite carbon, and so we get this pair of resonance structures where we have a carbocation on this carbon, so we have shared those, and then what we see then is that that double bond character is shared between both of those bonds. So partial bond, partial positive here, and partial positive there. So that is our resonance hybrid in this case. Once again, all three of those carbons are going to be sp2 hybridized. And if we compare these resonance contributors, these are equivalent since they both have essentially a primary carbocation, even though it's allylic. If we look at the second resonance structure, here we've got the major product being the second one because it fulfills the octet rule. So octet rule is pretty important. But the first one, of course, we had the second contributor was major because it had negative charge on oxygen versus carbon. Okay, so here's a practice problem for you to show how these two resonance structures are converted one from the other using electron arrows, and then draw a resonance hybrid. And you should further consider hybridization. If you'd like, that'd be a good thing to think about as well. All right, so that's just the refresher. We'll talk more about these in class, and we'll also talk about some fun new reaction, the Diels-Alder reaction, and addition of hydrogen halides to conjugated systems. We'll see you then.